Welcome to video 5 of regression analysis. Alright, let's pull up everything together now. We have been talking about the linear model. Given p independent variables with n observations in the model, the general form for the linear model will be y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth, beta p xp plus epsilon. And we have already seen the matrix representation of this linear model equation. This y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth till beta p xp plus epsilon is a mathematical expression to just say that the dependent variable y is related to all the p independent variables through some unknown coefficients betas. And then there is some error term e, something we can't really explain or measure directly. But at this point, this is just a linear model. This is not a regression model yet. Now, to turn it into a proper linear regression model, we need to make some assumptions on the error term. In this video, we are going to see what are those assumptions and what are the consequences of those assumptions on this dependent variable y. Okay, let's start. For any specific observation y, where I could be anything from 1 to n, we can write the model as yi is equals to beta naught plus beta 1 xi1 plus beta 2 xi2, so on and so forth, beta p xip plus ei. We have already talked about this equation in the last video, where this yi represents the value of the dependent variable for ith observation, xi1 represents the value of the first independent variable for the ith observation, xi2 represents the value of the second independent variable for the ith observation, and xip represents the value of the pth independent variable for ith observation. And this epsilon I, it is the error term for that observation I. It captures the part of yi that cannot be explained by these other independent variables in the model. Now, given any data set to you, you would have all the information about xi1, xi2, xip for all I from 1 to n. We would always have information about the independent variable in the data set. We would have the information about the dependent variable. But what about this EI? So we do not have any information about this error term E, and it captures the unexplained variation of the dependent variable. Now the question is, what do we do about this error term? Since we do not exactly know what the error term looks like, we make some assumptions about it to be able to work with the model. And the first assumption we make on error term is that the expectation of the error term is equals to 0. For each observation, for each I, expectation of EI would be equals to 0. Expectation of E1 would be 0. Expectation of E2 would be 0. So expectation of EI is 0 for all I from 1 to n. The second assumption we make on this error term is that the variance of EI is constant, and we denote that constant by sigma square. What does it mean? It means that the spread or variability of the errors is the same for all observation. In other words, it means that the amount of noise or randomness is consistent, whether you are predicting small or large values. Third assumption is that all EIs are independent and identically distributed. It means that the error you have from observation 1 is not related to any of the error term you have from other observations. So EI is completely independent of EJ. And the fourth assumption we make on error term is that all EIs have normal distribution. And for any specific observation I, where I can take value 1 to n, EI has normal distribution with mean 0 and variance sigma square. So we always make these assumptions on error term because we do not really know how error term would behave. It could behave in any random where. It represents the noise in the model. It represents the randomness in the model. Since we do not know how it might behave, we always make these assumptions on error term. Now, the moment we make these assumptions on error term, it would affect the dependent variable also. Now, let's try to understand how will it affect the dependent variable in the model. Given p independent variables, the linear model would look like this. The independent variables are viewed as controlled by the experimenter, so it is considered as non-stochastic. Once you get the data set, you have the fixed value for each xi. So we are considering xi's as non-stochastic. And from here, we can say that the independent variable x1, x2, x3, so on and so forth till xp are fixed and known in the analysis. The betas we have as the coefficient of x's are unknown but fixed values. Whenever you will have the data set, you will have the value for the dependent variable, you will have the value for the independent variable, but the value of the beta matrix, the coefficient matrix, would not be known to you. You would not know the value of the beta. But once you know the value, once you find the value of beta, therefore we say that these betas are unknown but fixed quantities. So on the right hand side, the only random part we have in the equation is the error term. And thus, the randomness or variability in yi comes only from ei, the error term. And since we have made assumptions about how the error term ei behave, those assumptions will directly affect the statistical properties of yi, like its expectation, variance, etc. And how does these assumptions on EI affects the statistical properties of YI? This is what we're going to see now. So the first assumption we made on the error term is that E of I for each observation is 0. So for any specific ith observation, this is the equation we have. Yi is equals to beta naught plus beta 1 xi1 plus beta 2 x2i2 plus so on and so forth, beta p xip plus ei. Xi's are non-stochastic, and therefore once you have the data set with you, you would know the value of xi1, xi2, so on and so forth till xip. We are treating all these xi's as the fixed quantities. These beta not beta 1, beta 2, so on and so forth till beta p, we do not know its value at the moment, but once we estimate its value, it will be a fixed quantity. Now let's take expectation both sides. If you take expectation both sides, on left hand side you would have expectation of yi, and on the right hand side you would have expectation of this entire quantity. We know the linearity property of expectation. Using that linearity property, we can write this equation as expectation of beta naught plus expectation of beta 1 xi1 plus expectation of beta 2 xi2, so on and so forth, plus expectation ei. Once you have the data set with you, you would know the value of xi1, xi2, xi3, xi4, so on and so forth till xip. All these xi's are known and fixed quantity. And these betas, we do not know the value of these betas at the moment. But once we find its value, it will not change. It will be a fixed quantity. So expectation of this beta naught would be beta naught. And this beta 1 xi1, beta 1 is unknown fixed quantity, xi1 is a fixed quantity. So if you multiply these two quantity, you still have a fixed quantity. Expectation of a fixed quantity of a constant is a constant. We apply this logic over here and we get that our expectation of beta naught would be just beta naught, expectation of beta 1 xi1 would be beta 1 xi1, so on and so forth. Expectation of beta p xip would be beta p xip. And we have made an assumption on error term that expectation of ei is 0, and thus expectation of ii is equals to beta naught plus beta 1 xi1 plus beta 2 xi2, so on and so forth, beta p xip. In general, given any p predictors, the linear model equation in general can be written as y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth, beta p xp plus e. As a consequence of the assumption that expectation of error term is equals to 0, we have that expectation of the dependent variable y would be equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth till beta p xp. The second assumption we have on the error term is that variance of EI is equals to sigma square. Let's see what consequence it would have on the dependent variable. So for any specific ith observation, we have this linear model equation. We take variance both sides. When we take variance both sides, on the left hand side, we have variance of II. On the right hand side, we have variance of beta naught plus beta 1 xi1, so on and so forth till beta p xip plus ei. We use the same logic as we used in the last property that xi's are non-stochastic. Since xi's are non-stochastic, once you have the data set, you would have the value of the p independent variables present in the model. Once you have those values, you're not going to change it on your own. So you treat those xi's as fixed quantity. Xi's are fixed known values to you. Betas are unknown, but once you estimate its value is not going to change. Its value will also be fixed. So beta naught is a fixed quantity, beta 1 unknown fixed quantity, xi1 a fixed quantity. So multiplication of these two fixed quantity will also be a fixed quantity. Beta 2 xi2 a fixed quantity, so on and so forth. You would have beta p xip as a fixed quantity, and we get variance of beta naught plus variance of beta 1 xi1, so on and so forth till beta variance of beta p xip plus variance of ei on the right hand side. Now we use a property of variance that variance of a fixed quantity is zero. Since variance of a fixed quantity is 0, beta naught is a fixed quantity, variance of beta naught would be 0. Beta 1 xi1 is a fixed quantity, variance of this second term would be 0. Beta 2 xi2 is a constant fixed quantity, variance of beta 2 xi2 would be 0. And so on and so forth, variance of beta p xip would also be 0 since beta p xip is a fixed quantity. And we'll be left with variance of ei. We have made an assumption on error term that variance of EI is sigma square. Therefore, as a consequence of that assumption, we get that variance of YI would also be equals to sigma square. Thus, for any ith observation, we would have that variance of yi is equals to sigma square, which means that the uncertainty in the model's prediction does not depend on the value of the predictors. In simpler words, the amount of noise or randomness is consistent whether you are predicting small or large values. The third assumption we made on error term is the EIs are independent and identically distributed. Let's look at this model equation for any given P predictors. Here, betas are unknown fixed quantities, x's are fixed quantity, meaning once you have the data set, you would know the value of all the independent variables and that will be fixed. You cannot really change it on your own. And EIs are the only random quantity present in the model. If we look at this yi dependent variable, the behavior of this dependent variable is completely dependent on what is present on the right hand side of the equation. Now, since betas and xi's are the fixed quantity, beta naught is a fixed quantity, beta 1 x1 is a fixed quantity, so on and so forth, beta p xp is a fixed quantity, the randomness in yi will come from the randomness we have on the error term. And since all EIs are IID, it will imply that YIs are also IID. The behavior of YI is completely dependent on the behavior of EI because all the other terms present in the model are fixed. And as a consequence of this assumption on error term, we get that YIs are also independent and identically distributed. The last assumption we make on error term is that EIs are normally distributed for each I. Again, for any given P predictors, YI can be written as beta naught plus beta 1 x1, so on and so forth, beta p xp plus ei, where betas are unknown fixed quantities. All xi's are fixed. EIs is the only random quantity. Therefore, The behavior of yi, which is completely dependent on all the terms you have on the right hand side, betas and xi's being fixed do not really affect yi. So the randomness again in y only comes from the randomness or noise you have in the error term. And since all EIs are normally distributed, we will have that YIs will also have normal distribution. And as a consequence of the assumption on error term that all EIs are normally distributed, we have that YIs are also normally distributed for each I from 1 to n. Perfect. So now we know the consequences of all the error term on the dependent variable. But wait, we are talking about the linear regression model in this video. What is a linear regression model? A linear regression model expresses the mean of the dependent variable as a linear function of the independent variable. That is, E of yi expressed as a function of only independent variables. And variance of yi is same across each observation. And how do we reach to this model equation? We reach to this model equation after we make those four assumptions on the error term. So the assumptions on error term are very, very important because we get this linear regression model once we make those assumptions on the error term.